Teacher Carlos Candid of Durham College states, "Better believe it. I've spent my entire life fostering a specific hypothesis of the universe, and presently the hypothesis is being tested. I welcome that, since that is the means by which we push ahead. That is the way we gain ground in science. The James Webb Space Telescope is toppling quite a bit of what has been considered truth in cosmology for the recent years. Another ultra-profound picture shows that we have committed errors in space science. The telescope that was expected to show us the principal stars of the universe is turning into an enemy of the past perspective and may present to us a totally different science. Not all scientists are shuddering in dread at the new realities. Numerous researchers invite the turns of events since it has for some time been certain that something was the matter with our old speculations. The errors in the estimation of the expansion pace of the universe alone ought to have shaken analysts alert a long time back. Yet, all things being equal of deciphering the admonitions accurately, they stuck to old hypotheses. The astronomical microwave background radiation, CMB, considered the most ancient light in the universe, was made around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen molecules. Specialists call this change reionization, which made the universe penetrable to light. The CMB was first found in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another sort of radio wave technology. This discovery was long viewed as quite possibly one of the most robust pieces of evidence for the Big Bang hypothesis, procuring Penzias and Wilson a Nobel Prize and a prominent spot in the history of astronomy. The CMB likely offers a depiction of the youthful universe, with little temperature fluctuations giving significant data about the conditions not long after the Big Bang. Researchers utilize the CMB as a solid imprint of the fundamental measurements of the material universe to gauge the expansion pace of the universe, among other things. The astronomer Edwin Hubble had previously determined this in the late 1920s, finding that far-off galaxies move away from us every which way and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the advanced measuring techniques available many years later when the CMB was found, which led to a recalculated expansion rate significantly lower than Hubble's original figure. Later researchers recalculated the rate once more, utilizing type Ia supernovae as standard candles, giving stable light that could be used as a reliable measuring point. The measurements within the CMB yielded an expansion pace of around 67 kilometers per second per megaparsec, while measurements utilizing supernovae yielded around 74 kilometers per second per megaparsec. What does this difference in determining the expansion pace of the universe truly tell us? Did you know that this error has been known since the 1990s? From that point forward, scientists have known or suspected that something may be wrong with the appraisal of the CMB, the measurement techniques, or the idea of the universe's expansion. The error between the different measured values of the expansion rate is known in science as the Hubble tension or Hubble strain. The ramifications of this tension are significant, showing that significant parts of how we might interpret the universe may be imperfect. For a while, specialists were confused. Since the James Webb Space Telescope went into operation, it has provided researchers with astonishing information that may now shed light on the issue of the expansion pace of the universe. Galaxies so old and mature that their formation should theoretically precede the Big Bang are disrupting old astronomy. Specialists no longer talk about inconsistencies or measurement differences. They discuss the greatest emergency in modern astronomy. Not only might the expansion rate be incorrect, but the entire idea of expansion or the Big Bang itself is being questioned. Webb's pictures provide evidence of a universe totally different from what we have long thought. The Hubble tension was the first warning. Specialists who still believed in old theories now face a problem. Do we, in fact, know anything about the universe? Numerous researchers stand on the remnants of their labor of love, investigating space with awe, grasping what they find, considering the emergency in science. We should ask ourselves what we genuinely know about the universe. To answer this, we need to understand how science works. Theoretical researchers use a complex web of mathematical models, exact data, and rational thinking to draw conclusions from the general to the specific. Their insight comes from a blend of observed phenomena, experimental results, and theoretical investigations. The term theory alone indicates that these are constructs and ideas, not absolute pieces of knowledge. The only practical information we have are the images telescopes provide, the sound waves and radiation captured with radio telescopes, and the latest data from neutrino measuring systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can separate the most ancient light into individual frequencies and analyze it in remarkable ways. Webb can show us the prevalent elements in galaxies more than 13 billion years back, how much mass they contained, and the number of stars in them. It can also reproduce the shape and direction of a galaxy's evolution. However, Webb can also have shortcomings. For example, it can't always determine with certainty whether we are seeing galaxies or black holes with enormous accretion disks that shine as brightly as a galaxy. We must face the truth that our science has long accepted too many possibilities as facts and ignored alternative explanations. Research has long been confident in its accuracy. The latest discoveries from the James Webb Telescope are significant pieces of information to replace theories with new insights, as has happened commonly in science. Researchers are currently awaiting new revelations, which are too astounding, and many scientists struggle to come up with new explanations. The new discoveries shake the foundations of our physics, frightening many scientists. Today's lessons of physics are still largely based on Isaac Newton's work from the 17th century. His laws of motion and gravity were the foundation of our physical understanding of this present world and the universe for hundreds of years. Newton's laws explain the movements of objects under ordinary conditions and work well on Earth. However, in space, his ideas required expansion, largely completed by Albert Einstein at the start of the 20th century. Einstein's special theory of relativity, published in 1905, changed our understanding of existence, showing that they are relative to one another and depend on the observer's motion. His general theory of relativity, published in 1915, expanded this idea with mathematical proofs of gravitational phenomena based on the shape of spacetime by masses like stars or galaxies. Einstein's theories and ideas were groundbreaking in many areas, but he also knew their limits. He knew his theories could never fully describe the universe and longed for a world formula, which he did not achieve. No other scientist has succeeded to this day. Where is the mistake? Wouldn't it be interesting to know where it lies? Michio Kaku, a famous astrophysicist from the USA, said in an interview that addressing this issue would certainly win a Nobel Prize. How about we investigate the facts scientists could have overlooked, possible misinterpretations, or whether our telescopes are at fault? Dark matter and dark energy are at the top of the list of suspects for the real causes of the cosmological crisis. Our current models of the universe include concepts that dark matter and dark energy make up around 95% of the universe. However, neither has been directly observed, and their true existence has never been demonstrated. They might not exist at all, requiring alternative explanations for the universe's expansion and dynamics in galaxies, or they could have properties we don't yet know. One thought is that the actual properties of dark matter and dark energy have changed over time, potentially showing some sort of evolution. Gravity is another idea to be tested. This force, causing attraction through mass or curvature in spacetime, has not yet been demonstrated. The ideas of spacetime curvature largely originate from Einstein and have been validated multiple times. However, we can't rule out the possibility that gravity has unexpected properties compared to what we thought, or that another effect causes the gravitational pull between objects. Throughout the years, certain values have been established in cosmology and astronomy as universal constants. The study of the universe has always been a journey marked by our constant quest for understanding and discovery. From ancient civilizations observing the stars to advanced space telescopes exploring the depths of the universe. Every advancement in technology and theory has uncovered new secrets while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of our scientific progress, promising to revolutionize our understanding of the universe's beginnings and evolution. Launched with remarkable capabilities, JWST represents a leap forward in observational astronomy, capable of probing deeper into existence than ever before. One of the primary goals of JWST is to study the cosmic microwave background (CMB) radiation with unparalleled accuracy. The CMB, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe as it existed just 380,000 years after its birth. This primordial radiation carries crucial information about the universe's early conditions, including its temperature fluctuations, which are essential for understanding the formation of galaxies and large-scale structure. The disparity in the measured values of the Hubble constant, known as the Hubble tension, has been a persistent issue in cosmology. While the CMB measurements suggest a lower expansion rate of the universe, observations using Type Ia supernovae and other cosmological probes yield a higher value. This tension implies that our current models may be incomplete or that there are fundamental aspects of the universe's expansion dynamics that we have yet to grasp. Beyond the Hubble tension, JWST has the potential to shed light on other cosmological mysteries, such as the nature of dark matter and dark energy. These elusive components make up a significant portion of the universe, yet their true nature remains unknown. By observing the formation and evolution of the earliest galaxies and the properties of dark matter, JWST may provide critical insights into these enigmatic phenomena. The implications of JWST's findings are profound. As the telescope uncovers new details about the universe's infancy and growth, scientists will need to reassess and refine existing cosmological models. This process may lead to paradigm shifts in our understanding of fundamental physics and the universe's history. Ultimately, JWST's contributions to cosmology will enrich our comprehension of the cosmos, challenging existing theories, and paving the way for new discoveries that could reshape our view of the universe.